Good afternoon, everyone. I'm Wentao, and I'm a final year PhD student from the Hong Kong University of Science and Technology. Today, I'm going to share with you our recent work, EarSpiro. In this work, we are using a cost-efficient method to predict a patient's lung functions. So why are we interested in this topic? So why are we interested in this topic? First, according to the WHO, COPD is the third leading cause of death as of the year of 2019. It is chronic because it cannot be fully cured. And for a patient, he or she requires long-term management. So to fully support the patients, we need to have their lung function assessed quite regularly. So the spirometry is the golden standard for lung function assessment. So during this test, the user needs to use a spirometer, which measures the airflow in and out from the user. And during the test, well, let me just show you the demo video of a standard protocol of the spirometry test. As you can see, the user first breathes normally through the device, and then he gives a full inhalation followed by an explode of exhalation, then followed by a full and maximum inhalation. So these three steps gives the result of the spirometry, the flow volume curve. And this curve is representative of different types of lung conditions. So here a short summary. So first, the user inhale fully, then exhale with his or her maximum effort, and then inhale with maximum effort. And the resulting flow volume curve have different shapes that representing different lung conditions. For example, if the patient is with asthma or COPD, the shape will be kind of convex. Let me point it for you. A little bit convex than the normal subject, and apart from the curve itself, the doctors always extract some lung function indices from the curve. For example, the PEF, the FEV1, and the FVC. This set of lung function indices can also represent the patient's health conditions. And again, some patients may need to do this spirometry test on a daily basis. However, the problem is not all patients can afford that. So this is a typical home-based portable spirometer, and it costs around $5,000 US. And also for the spirometer that used in the hospital, the cost may up to hundreds or thousands of US. So this conventional method may not suitable for every families. So is there any cost-efficient solutions? Well, there is in the research field. So researchers are trying to leverage common off-the-shelf devices like smartphones to conduct spirometry. So these work are all common off-the-shelf method. However, the common limitation of this work is that they can only extract a very limited set of lung function indices rather than the entire flow volume curve. Plus, this method have no inhalation measurement. So in our work, we're trying to bridge this gap. We're trying to propose a cost-efficient method that can that can reliably track the entire flow volume curve, including both the expiration stage and the inspiration stage. So our observation to solve such a problem is that recent research have shown that there is a certain correlation between the airflow sound and the actual flow rate. So imagine if we have an audio sensor that is accurate enough, that is stable, and really close to the tracheal area, for example, located on the earphone, then we're able to interpret the recorded airflow sound into the flow rate, therefore predicting the entire flow volume curve. So this figure shows such kind of correlation. We can see that the first two lines shows the actual audio sound, and the third line is the correspondingly ground truth of the flow rate. So we can see quite clear the correlation. So to realize such a system, we propose EarSpiro. We embed microphones on one pair of earphones. The earphones record the real-time audios or when the person is performing spirometry, and we designed a data processing pipeline to predict the flow volume curve from the recorded audios. So the first step for the system is to accurately locate the expiration stage and the inspiration stage. So it may seem not that difficult on this given example, but it will be a little bit harder when it comes to inspiration signals, especially for the patients that with limited lung functions. For example, can you tell where are the inspiration stages from these two examples? It is a little bit harder than you think, and it is difficult without the help of the actual ground truth. But luckily, we observed that no matter how weak this inspiration signal is, there can only exist 3 types of signal in a given audio segment. First, inspiratory signal. Second, noise signal. And third, a north signal, which means there is neither noise signal nor the inspiratory signal. And interestingly, these 3 types of signals have distinctive frequency frequency features. So we can just use a really lightweight clustering algorithms, for example, k-means, to segment one type of signals from the others. So here are the results of the clustering. All the time steps are clustered into one of these 3 categories. And the category that belongs to inspiratory signal can be easily identified by applying a screening criteria. So following that, we designed a deep learning network that takes the segmented expiratory and inspiratory signal as the input and predict the flow rate. And we plot the predicted flow rate and the predicted lung volume in the flow volume plane to give the final flow volume curve prediction. And in addition to that, we enable EarSpiro on daily objects such as a funnel with minimum user efforts. We use a decoder network to synthesize the training labels and user transfer learning to transfer the model on the funnel. So please refer to our paper for more detail. So we conduct a user study on 50 subjects, including 7 patients. I'll say there are some of the stats, and there are some other examples. And the last slide is reserved for me. So I'm about to enter the job market next year. So if you have like academic job openings, and you are willing to have me on your team, so please contact me and we can chat. So thank you.
Mic check. Ooh, I can hear myself. Hi, Alex from the University of Toronto. So really interesting work. When I've seen spirometry, a lot of people move their head when they're doing the spirometry effort. Do you see that? Does that affect the signal you're getting, or is that kind of a non-factor because you're using the in-ear microphone?
Well, actually, when we're collecting the data, many of the patients have intended body motions, but I think they have little impact on our system because the ear wear on the eye is relatively, stable. The unintended body motion can hardly affect the quality of the audio recorded by the earphones. So I think that is not a big deal.
Thanks.
Thank you.
So how do you train the deep learning model? Is it individual focused, or is it trained on a data set and then you?
Yeah, we use a leave one subject out validation. Okay. So okay. We have 50 subjects. Mm-hmm. We use 49 of them for training and 1 for testing.
Okay.
Yeah, thank you.
Yeah.
No, we don't need to personalize it.
Mm-hmm. Okay.